Everyone, thank you, Mehmet, for introduction. I would like to start by thanking Ali, Yangchi, and Mehmet and Johnson. Thank you very much for organizing this seminar. I'm going to talk about nitric oxide releasing nanomaterials for cardiovascular applications. As you know, the use of nanomaterials and materials have been pioneered in the field of cancer and infection, but remains infancy in cardiovascular diseases. So our focus is on delivering the most important and powerful signaling molecule, nitric oxide, for cardiovascular diseases. So first of all, a little bit about the history of nitric oxide. It got Nobel Prize in 1998 for the role of nitric oxide in cardiovascular diseases. Since 1880, glycerine trinitrite, GTN, a drug has been used for the treatment of angina and heart attack. But no one knew why GTN works and why it relaxes blood vessels. So these three scientists, they discovered that this is actually nitric oxide, which relaxes your blood vessels. And science also declared as nitric oxide as a molecule of the year in 1992, and they also published that no news is a good news. So, and there are, after the discovery of nitric oxide, there were many supplements introduced as a nitric oxide donor, like L-arginine, L-citrulline, and many other donors. So we are using nitric oxide as an exemplar because it's the most powerful signaling molecule, a gasotransmitter in the body. Oxygen is not a gasotransmitter because it is not produced internally. So nitric oxide is number one gasotransmitter. So it is produced by the enzyme called nitric oxide synthase. So there are three forms of nitric oxide synthase: endothelial nitric oxide synthase, which is produced by the endothelial cells in the cardiovascular system, and then neuronal nitric oxide synthase, which is produced in the brain, and then inducible nitric oxide synthase, which is produced by macrophages, which also plays a key role in inflammation. Nitric oxide levels decline with age. At the age of 40, at the age of 30, you got 100% production of nitric oxide in your body, but at the age of 40, you only got 60% nitric oxide production left in your body. So what are the clinical consequences of insufficient nitric oxide production? So it leads to cardiovascular diseases, bacterial biofilms, cancer, eye diseases, and many other human diseases. So the role of nitric oxide. So there is a blood vessel in the corner on the right hand, you can see. So there is a lining of endothelium in the endothelial cells, and in the blood vessel. And these endothelium has trillions of endothelial cells. They continuously produce nitric oxide, which relaxes your blood vessels. It is a vasodilator. It also lowers your blood pressure. And also improves blood flow, and it is also has platelet aggregation effects, anti-inflammatory, and in myocardial infarction, it lowers the production of reactive oxygen species, so which is very important for heart attack. And then nitric oxide itself is not anti-cancer or antibacterial, but the byproducts of nitric oxide are antimicrobial and anti-cancer. For example, when nitric oxide interacts with superoxide, for example, in tumors or in different bacteria, it produces peroxynitrite. And peroxynitrite is also another free radical, so which is highly toxic. Thus, actually, it inhibits bacterial growth, and it modulates immune system, anti-inflammatory, and it also inhibits biofilms. And similarly, it plays an important role in cancer. It suppresses tumor progression. So there are already many drugs in clinic based on nitric oxide. So, for example, it is used in the labor room for the newborn babies and also for the women. And it is also used, as I earlier mentioned, in the form of GTN for the treatment of acute angina. It is also used for eye hypertension and heart failure and many other basically diseases. So there are already many drugs available in clinics. So why do we want to develop new drugs? So because one option is, so we can simply take nitric oxide supplements, so which are also very cheap and they have very low toxic effects. But the problem with all these drugs and supplements is that they are not targeted to the site of action, and they also have nitrite, for example, nitrate tolerance, and the other effects are headache, nausea. Why? Because of the short biological half-life of nitric oxide, which is only 2 to 5 seconds, and also short diffusion rate. So we can overcome this problem by using a carrier, a nano carriers, to deliver nitric oxide at the right place and right time. So we hypothesized that we can use graphene as a carrier of nitric oxide. So why to use graphene? Because graphene has high specific surface area and it is also easy to synthesize, and we can also make it stimuli responsive, the stimuli which are key characteristics of damaged cells. So we primarily use graphene oxide because graphene oxide has many functional groups like carboxylic functional groups, so which we can utilize for the functionalization with different biomolecules. And this is a microscopic view of graphene. So that's a sheet-like structure. So now coming after a little bit of background, so now coming to our approach that what we are currently doing in our group. So we are using two types of approaches. One is a catalytic approach. So there are already nitric oxide production in the body. So by a patient, there is a low production of nitric oxide. So a patient has a massive production of nitric oxide sources, but they don't have those enzymes to convert those sources into nitric oxide. So we can use these nanomaterials, nanoparticles, as a catalyst, and they can catalytically decompose those NO sources into NO. So that's the one approach. And the other approach, that's basically catalytic approaches for long-term use, for example, stent, where we want to use stent for like 2 years, 2 to 3 years. But for short-term NO release, for example, for heart attack or ischemia, reperfusion injury, we only want to deliver NO just for 3 to 5 minutes. For that, we can use directly NO gas or different other NO sources. So that's non-catalytic approach. So where we store nitric oxide into the pores of these materials and we release them in response to a stimuli. So what are the applications we are working on? So one is the cardiovascular implants, for example, vascular stent, and then the others are injectable nanoparticles. That's primarily for ischemia reperfusion injury. So today I'm going to talk about three aspects. So one is the NO generating graphene. So that's basically a catalytic approach. So this is a normal human artery, blood vessel. So as I earlier mentioned, so there is endothelium. Endothelium has endothelial cells, which is continuously producing nitric oxide, which is a free radical and a vasodilator. In a diseased human artery, there is a narrowing of arteries. How this is treated? By the use of a stent. So there are two generations of stents, bare metal stent and drug-eluting stent. So bare metal stent is made up of stainless steel, and it has a problem of in-stent restenosis. So there is a narrowing around the stent again, so which is called in-stent restenosis, also inflammation around the stent. So then in 2008, drug-eluting stents were introduced, where they use chemotherapeutic drugs onto the surface of stent. So I work 1 day in the cardiology ward per week, and we see the patients that actually, when they implant these stent, so how much drug is actually delivered to the coronary arteries. So only 20% drug is delivered to the arteries. 80%, up to 80% drug is lost during the delivery. So there is a catheter which is used to, that's basically a wire used to deliver the stent through the veins to the coronary arteries. And there is a balloon at the edge of the catheter that actually release the stent. So what does stent exactly do? So stent basically reduces the proliferation of smooth muscle cells. And it is also, because it's a chemotherapeutic drug, so it also basically has severe toxic effects as well. So we hypothesized that if we use nitric oxide based coated stent, so that could, in addition to basically the drug eluting stent, because we also want to improve the proliferation of endothelial cells. So for vascular healing, so first of all, we need endothelialization. And endothelialization, drug eluting stent, they don't have any effect on endothelial cells. So they only have effect on smooth muscle cells. As NO has actually both effects, so it can improve the proliferation of endothelial cells, it can reduce the proliferation of smooth muscle cells. So we are using basically the NO sources from the bloodstream. So this is an approach that if we use amine groups on top of the graphene, and then we coat graphene onto the stent, a layer by layer coating. So the first layer will come interact with the bloodstream, and then the second layer, then the third layer. So that's how we can make it a renewable generation of nitric oxide over a long term. So what's the mechanism? So this is a branched amine group, so which has primary amine groups and also, of course, secondary. And then this is a nitric oxide source called S-nitroglutathione, GSNO, in the bloodstream. So the amine groups act as a nucleophile, and it attacks the electrophile group of GSNO or RSNO. So that's S-nitrothiols or S-nitroglutathione. And once the nucleophile attacks the electrophile, it splits nitric oxide. So that's the chemistry behind it. So why not to use polyethylene amine on its own? Because if we use amine groups, free amine groups, so the problem will be that because there is nitric oxide production are different at the nitric oxide sources, as I mentioned, in the bloodstream, so they can make nitrous amine, and nitrous amine are carcinogenic. So we don't want to produce nitrous amine in the coronary arteries. So that's why we want to have a controlled system where the amine groups can interact with the nitric oxide substrate in a controlled manner. So that's the basic characterization. I'm not going into the detail of XRD, Raman shift, but that's basically just to show the amine groups have been successfully conjugated with graphene. So we also use polyethylene glycol because it improves the dispersibility of graphene, and it also can also improve the retention time of these coatings in the circulation. And then TGA, so just to show that how much basically polyethylene amine and polyethylene glycol have been conjugated onto the surface of graphene, and then also water contact angle to show the dispersibility, the improvement in dispersibility of graphene. And then coming to the nitric oxide generation profile. So first of all, this is by using electrochemical sensor. So where we use a real-time release measurement to see that if GSNO as an internal source in the bloodstream, so if it can produce NO over time. So we just selected 10 micromolar. So that's actually in the blood vessel producing every hour. So we see that it also produces nitric oxide, but the amount is not therapeutically relevant. So, but if we use it with unconjugated graphene and then with conjugated graphene, so we see that we can release nitric oxide up to 8 micromolar out of 10 micromolar. So that's also therapeutically relevant. And then we show using ozone-based chemiluminescence how much nitric oxide we can produce. For example, first just from GSNO, 10 macromolar, and then using with conjugated graphene. And we published this paper, Ali and Yang Qi, recently in Applied Physics Reviews. And then we coated these materials onto biodegradable stents to see whether graphene has been successfully conjugated onto the stent. But because recently there has been a lot of controversy around biodegradable stents in the cardiovascular diseases, so that's why we also used it on bare metal stent to show that basically our coating system is feasible and it can be used onto different cardiovascular implants. So from scanning electron microscopy, so you can see that we can clearly see the sheet-like structure of graphene. And then we also looked at the hydrolytic degradation of coated and uncoated stents for biodegradable stents to see whether the coating affects its degradation or not, which it doesn't up to 60 days under basically under accelerated conditions. And then we look at after 60 days whether our amine groups and graphene still exist onto these stents or not. So we use basically an amine assay to look at the quantification of these groups. And then we also look at the morphology of these stents to see whether graphene and amine groups exist after 60 days or not. So which we can see that we can still see that they are degrading, but graphene is still present onto the surface of stent. So this is another work with a joint PhD student from UNSW. So we also use the system on catheters, basically for infections, catheter and cannulae, which is used for the prevention of biofilms. That's not really the objective of this talk, but I'm actually just want to give an example that this system can also be used for other implants or devices as well. And using scanning electron microscopy, so we show that the material has been successfully conjugated and also look at the coating thickness. And then we also, because these devices are generally stored over long term, so we also want to see whether if we store this device under just like at room temperature, so whether the anode generation ability will still be practically possible or not, and whether it will be clinically therapeutically relevant or not. So we look at the anode generation ability, although over long-term storage, it has been decreased, but not significantly. So we can still see, this is again using electrochemical sensor to show the real-time release, the generation of nitric oxide. And then we also look at the stability of these basically anode generation under different conditions. For example, if we autoclave them and if we measure anode after 24 weeks, and if we put them under light, and if we measure anode generation ability after 24 weeks. And then we look at the anti-inflammatory effects. We recently got a lot of interest in inflammation because vascular inflammation is a very big problem, of course, but also there is not any drug available for vascular inflammation in particular. So first of all, we just use the cells. So you can see, and then because in macrophages, so there are 3 stages. So there is a 1M0 stage, so when there is no any stimulation. And then there is a M2 stage where you stimulate using LPS, the macrophages, and then you activate different pro-inflammatory cytokines. And then there is a M3 stage, so where you stimulate them to activate anti-inflammatory cytokines. So in this case, we look at this, first of all, TNF alpha and IL-6, and we show from cells cells on their own, they don't really produce any TNF alpha. The same applies to IL-6 as well. And then if we stimulate them with LPS, so there is a massive production of TNF alpha. And if we use the GSNO, so that's the source of nitric oxide, and then we use the coated device, the coated catheter, so we can see that there is a same level of TNF alpha as compared to the unstimulated macrophages. So because macrophages also produce massive nitric oxide, so we also use nitric oxide inhibitor to show that these effects are genuinely arising from our formulations, not from the cells. And then, okay, so we see that basically there is an effect and there is a reduction in these markers. So why? As we are claiming that this is because of nitric oxide, so then we measured nitric oxide using grease assay to show that the coated device has a higher production generation of nitric oxide. Another study on nitric oxide releasing graphene. So these next two studies are about injectable particles which we are using for myocardial infarction and ischemia reperfusion injury. So first of all, just a little bit background about ischemia reperfusion injury. So when a patient has heart attack, so there is an episode of reperfusion right after the heart attack. So that's called ischemia reperfusion injury, and there is no any treatment available for the prevention or protection of ischemia. And it is clinically established, and there are already 2 drugs which have passed all clinical trials by a group from University of Cambridge. So they developed nitric oxide-based drugs for ischemia. So if you supply nitric oxide at the time of reperfusion, immediately after heart attack, so you can reverse the heart attack. So that's why it's highly important. And most of the time, we can also say that the patient is not dying because of heart attack. The patient is actually dying because of the reperfusion. And so what's the difference between our drugs and the drugs recently passed the clinical trials? Because they're directly using nitrite to produce nitric oxide. They're not using any targeting approach, while we are using ROS responsive, reactive oxygen species responsive nitric oxide, which is directly targeting mitochondria. So this is based on acidified nitrite. So first of all, this is a porous graphene oxide, so which has pores. So we introduce pores into graphene so it can carry more amount of molecules, gases. So then we conjugate it with cysteamine, so which has thiol groups. And then those thiol groups have been conjugated to acid nitrite, sodium nitrite under acidic conditions. So then we call it S-nitroso-cysteamine functionalized graphene. So what is acidified nitrite? So there are 2 sources of nitric oxide in the body. So the one I just mentioned that is produced by nitric oxide synthase. The other one is the dietary nitrite. So the green leaves are different foods you eat. So there is a gut bacteria which reduces the nitrite, basically dietary nitrite, into nitric oxide. So we use the same approach. Basically, the whole nitrite under acidic conditions, hypoxia, it is reduced into nitric oxide, and we can use the same approach to conjugate with nitric graphene. So we didn't use direct NO gas because the problem with direct nitric oxide gas is that it's not stable and you can't store it over long term. So that's why we are developing many different approaches as a nitric oxide sources. Oh, sorry. Okay, so that's the basic characterization to show the XRD with cysteamine and then with nitrite. So there is a shift in XRD peaks, and then also FTIR to show the introduction of new functional groups, and then BET specific surface area to show that porous graphene oxide has higher specific surface area in comparison to its counterpart graphene oxide. And then scanning electron microscopy, transmission electron microscopy images to show the sheet-like structure, and then to also show the the functionalization is not affecting the sheet-like morphology of graphene. And then nitric oxide release profile with ozone-based chemiluminescence, first of all, to show the total release. So if we use 250 microgram per ml of porous graphene oxide, so we can produce around 15 micromolar of nitric oxide. So that's highly relevant. If we use 1 milligram, that could be a little bit toxic to the non-disease cells, but it is around 30 micromolar. This is a real-time release that from 250 micromolar of 250 microgram per ml of graphene, how long we can produce nitric oxide. That's up to 140 minutes. There are also many controversies around nitric oxide detection methods. So we also developed a novel protocol using electron paramagnetic resonance, EPR, using a spin trap method. So where you use a spin and it forms an adduct with the nitric oxide and it gives you a 3-line spectra of nitric oxide. So we show that the spin trap on its own doesn't has any nitric oxide and neither porous graphene oxide or cysteamine functionalized, but once it's conjugated with snow, it does has. And then we look at the endothelial cell proliferation, and we show that under different concentrations, you can see that there is a higher proliferation of endothelial cells because we want to improve the proliferation of endothelial cells so they can relax the blood vessels. And then we also compare it with unmodified graphene and also if we use acidified nitrite on its own. So we see that they also improve the proliferation, especially as acidified nitrite, but because when we are carrying nitrite with graphene, so of course we are carrying higher amount and also in a controlled manner, so that gives a better proliferation. So then the first one was MTT assay and figure B, because MTT assay is not really a proliferation assay, so we use BRDU, DNA proliferation assay, to show that this is definitely proliferation of cells. So we got pretty much similar results. Okay, so we see the readout that, okay, so endothelial cells are proliferating. Why? So then we use nitric oxide sensitive dye, fluorescent dye called DEF, to show that whether nitric oxide is inside these endothelial cells or not. And we show that it is. So because endothelial cells, they also produce nitric oxide. So we also use nitric oxide inhibitor called L-NAME to stop the production of nitric oxide from these endothelial cells. So just to confirm that these effects are arising from our formulation. Okay, so nitric oxide inside the cell. So where does graphene go? So then we used Raman imaging mapping to show, because graphene has a very strong Raman signal. So we show that the bright green signals show the uptake of graphene. And then we look at the smooth muscle cell proliferation because we want to reduce the smooth muscle cells, the proliferation of smooth muscle cells. So we show that using MTT assay that it is reducing the proliferation of smooth muscle cells. So now, because this is MTT cell viability assay, so maybe graphene is toxic to smooth muscle cells. So that's why the cells are failing to proliferate. So then we use BRDU assay, DNA proliferation assay, to show that this effect is genuinely coming from the proliferation, not from the toxicity. And then there is a downstream signaling pathway in smooth muscle cells. It's called cyclic GMP. So then because nitric oxide is actually produced in endothelial cells in a blood vessel. So there is endothelial cells first, and then there are smooth muscle cells, and then cardiomyocytes. So it is produced from endothelial cells, then it transfers to smooth muscle cells, and then from there to the cardiomyocytes. So its major primary source is actually endothelial cells. So once it goes to the smooth muscle cells, it actually goes through a downstream signaling pathway called cyclic GMP. So we looked at the cyclic GMP, whether our formulations have ability to increase cyclic GMP. If cyclic GMP is increased it means that there is production of nitric oxide. And we see that with these formulation in comparison to its unconjugated and also acidified nitrite as a source, there is a better production of, there is an increase in cyclic GMP. So the same stuff that wired because of the uptake of nitric oxide, the localization of nitric oxide in smooth muscle cells, and then also the Raman imaging mapping to show the graphene uptake by smooth muscle cells. And then because as I also mentioned in the very beginning, that nitrosamine production is a very big problem with most of the drugs based in clinic, because nitrosamine, because there are nitric oxide sources, and then you are also supplying nitric oxide, and then there are also free amine groups in the body as well. So they can quickly make, because nitric oxide is a very aggressive gas because it's a free radical, so it can make nitrosamine. So then we look at the production of nitrosamine in endothelial cells and smooth muscle cells. Figure is endothelial cells, and we see that basically if we use SNAP. So SNAP is actually another drug which is also used in clinic for cardiovascular diseases. So first we use SNAP, and we show that if we use SNAP, so it definitely produces nitrosamine. And then we use SNO with graphene, and then we show that basically it doesn't produce any nitric oxide. So we developed a novel assay to measure nitrosamine, because there are more than 20 forms of nitrosamine. So anyways, so then we look at the anti-inflammatory effects against raw macrophages. We show that our formulation under different concentrations, it's very much viable with the macrophages. And then we stimulate them. That's so the first one was M0 stage, when you don't stimulate these cells, and then M1 stage when you stimulate them with LPS, and we look at the effects. And then we show using grease assay that this effect is confirmed by the production of nitric oxide. So that's a very quick study, because as an engineer, so you know that basically there are different stimuli are used basically, for example, light, ultrasound, or X-ray. And similarly, there are stimuli in the disease cells, for example, low pH, hypoxia, or overproduction of reactive oxygen species at different enzymes. So we recently started this team to make supramolecular assemblies. So where you basically use different peptides, and you non-covalently you attach those peptides to the nanoparticles. And those, because they are non-covalent, so they will be disassembled when they're interacting with those enzymes or reactive oxygen species. So we use diphenylphylline, that's a peptide, dipeptide, a short peptide that's also already present in human brain. So we use that peptide, and we show that under acidic conditions, if you look at neutral, so you see a sheet-like structure, but if you look at acidic conditions, so you can clearly see that these assemblies are basically disassembling. So then we show that under neutral pH, this supramolecular assembly is not releasing any nitric oxide, but under acidic condition, it does. So then we using electron paramagnetic resonance, and then we show the average peak area calculated from EPR to show that basically how much NO is actually released under different pH, and you can see that it is primarily released under acidic conditions. This brings me towards the end of my talk. I would like to acknowledge my colleagues from Oxford, Professor Keith Cannon. So he is one of the top players in the field of nitric oxide, and interventional cardiologist who was also involved in drug-eluting stents in 2008. and also colleagues from Terasaki, Ali, Yangchi, and Ali R, I don't know, Ali R or Ali H, and other colleagues from different parts of the world, and also my funders. Thank you very much indeed.
Any questions for Tanveer?
It's an interesting talk. So especially the layer by layer coating of two molecules you mentioned. One is SNAP, another one is GSNO, something like that. So my question towards Louis is like how the sustained release is possible, how long it is possible, or what is your major breakthrough you have developed in your systems compared with the existing NO releasing platform?
So basically, the injectable particles, for example, as nitrocysteamine, SNO cysteamine functionalized graphene. So we are using it for ischemia, reperfusion injury, and we only want to deliver NO for very short time. For long-term release, so we are using NO generating approach. So that's basically we are using amine groups. We can also use thiol groups, which will be they will be converting NO sources from the bloodstream catalytically, because the patient, they have massive production of those sources, but they don't have NADPH enzyme that actually convert those sources into nitric oxide. So that's why for long term, what we think, what I've been discussing this with many colleagues who've been working in this area over the years, and because there are already many drugs in clinic, but the real challenge is to make it like for stent application, a vascular bypass graft. So the challenge is that you can't have encapsulation of NO source for 2 to 3 years. So that's not really practically possible. So that's how we bring this idea of NO generating.
Yeah, usually like a copper mediated
that's the very traditional,
copper
the
2 plus
copper mediated.
NO release is possible.
Exactly.
So Elizabeth Brisbios and Hitesh Khanda, they were mainly working on this kind of SNAP-based molecules.
Yes.
They have conjugated inside the catheter is for like a long time release and everything. So what was the main difficulties with the GSNO and SNAP conjugated polymer
Okay.
coating? So what was the main difficulty?
So basically, because G-SNO and SNAP has been extensively reported in literature for coatings as well, but these are actually the sources of nitric oxide, but they're not directly nitric oxide. So, but the problem here is if you use G-SNO, you have to use GSH as well. So because GSH will actually convert G-SNO into NO. And same applies to SNAP. So you always need actually a catalytic agent. So that's why, so what we are doing, so we basically have the agent on the device and we are utilizing internally produced, endogenously produced these molecules sources. So the real challenge with this G-SNO and SNAP is that you always need actually another molecule, another enzyme to basically convert, to basically release NO from those sources if you're conjugating them with nanoparticles at devices.
So if we conjugate this SNAP or GSNO to the any kind of polymer, do you think it will withstand for more than 7 days or 10 days? Or what is your experience?
Yes. So with the G-SNO and SNAP, you can definitely go up to 3 to 4 weeks. That's what we have done. But more than that is actually, then it becomes very difficult. And then the other thing is that basically GSH could also be a good approach because, for example, in many diseases, GSH is also overexpressed. So that's how you can also make it selective. For example, if you're doing G-SNO coating onto a device and you know that actually that disease has actually, for example, biofilms, they have overexpression of GSH. So for that kind of system, disease model, that could be excellent. Because, but in cardiovascular system, because GSH is overexpressed, but not as overexpressed that you can actually use it as a stimuli.
Okay, last one more questions. Like initially, the first few slides you have described the significance of NO for different applications, including the biofilm or like a neurological disorder or like cancer or cardiovascular things. So each organ or each place, maybe the NO releasing will be different because as you mentioned, the cardiovascular, we need to do in 5 seconds or 10 seconds. That is necessary. In the case of biofilm, you may need like a prolonged release to deplete the biofilm. For brain, for a microvascular endothelial cells, if you want to proliferate more, so you need to do a sustained release. Do you have any comment about that one? How to control the release in different body parts?
So there are actually groups from Michigan University and Georgia University. They're working on these biofilms models. Mark Merhoff. So he actually started this polymer field for nitric oxide releasing. But they haven't actually translated that. They're using different polymers, different materials, and then they're showing the efficacy, but they're not actually taking one. I'm not criticizing, of course, as a material scientist, we also used to do this, that take different nanoparticles because you already have a system developed. So basically you just show. But if you want to take it forward, so then I think there are so many different translational barriers. And with G-SNO, I'm not against G-SNO or SNAP, but because one of the major criticism is also about nitrosamine production, which we don't really want. And but actually for nitrosamine and also peroxynitrite. But for biofilms, it's good because for biofilms, you need actually toxic bioproducts. So that's how you will inhibit the biofilm. So I think the problem with biofilm is that with nitric oxide releasing systems, so people have shown that it disperses biofilm. It is actually killing the bacteria, but they haven't shown the downstream signaling pathway of nitric oxide. So that how exactly it is happening. So that's, I think, the fundament. Of course, if it is therapeutically efficient, it's good. So sometimes it works. But I think as a basic scientist, so we also want to see the mechanism that actually how it works. So we have a program grant with one of my colleague, Eleanor Stride. So she is running a very big program on nitric oxide for biofilms. And we are looking at the downstream signaling pathway, that how actually it is happening. And we also showing the localization of NO in bacteria and all these, basically it's different compartments.
I have a quick question. How do you deal with clearance of graphene from the body?
Yeah, so I think that's a very good question, and it's also very important for and valid for not only for graphene but also all these nanoparticles. We have studied the graphene oxide clearance and distribution, biodistribution in different organs, and as you know, that basically it's biodistribution, targeting, and excretion. Everything depends on the surface chemistry and the size of these particles. That's what we always write in papers. But going towards like the translational aspect, so because majority of the work actually comes from small animal models. So if you look at the cardiovascular system, so that's not really relevant to the small animal models because the human arteries are entirely different to these mice. So they are very relevant to like pigs, horses. So right now, actually, we recently got one funding from Wellcome Trust to develop these actually stent work and the clearance pathways of injectables in large animal models. So I can't answer this right now, but that's what we are working on it and very much looking forward to it.
Other questions?
A corollary to the question is some of the toxicity that has been reported with graphene nanoparticles, a long-term accumulation in organs like the liver. Is that better for graphene oxide that you're using? Do you know if there is a difference?
So there is a very recent study from University of Manchester. So that's where graphene was isolated in the first place. They just published a paper in Nature Nanotechnology, the first human trials of graphene exposure. So they show that actually graphene oxide is safe and at certain concentrations. So of course, if you use higher concentration, that will make it toxic. But small concentrations could also be highly toxic. But they show that up to 500 microgram per ml is safe to use. And so when we talk about different toxicity concerns of graphene, so because it's a carbon-based material, so carbon is generally considered safe. But actually, we also talk a lot about its sharp edges of graphene, but actually because it's too small, it's too tiny at the nano size, so those sharp edges, they don't really encounter with different kind of like cellular or tissue at the tissue level. So I'm not advocate for graphene, but actually because we're working on it and we believe that it definitely we need some more time to for the translational aspects.
Thank you.
Thank you very much.
Thank you for your talk. So I have a few questions already related to the clinical application of this type of technology. So the first one is like, what are really therapeutic level of NO, knowing that, its half-life is so low? So what is the, therapeutic level, both, I guess, locally in your case or systemically? Then
I think I can answer one by one. Okay. Otherwise, I have to start from the other way around. So that's very interesting question. So how much actually we want to deliver NO. So this level will exactly be the same how much endothelial cells are producing nitric oxide continuously per minute in the body.
Do we have a number? Because again, so this is where my second question comes into place, is that of course, endothelial cells are producing NO, but then in the case of coronary artery disease with arteriosclerosis, then those plaques are also producing ROH, which will scavenge your NO at the same time. So then, like when you say what is the local amount that like the endothelial cell will produce, is it that in a healthy state, disease state, and really how that delivery, when it's happening with the stent, for example, don't you think the NO is just going to flow with circulation and go elsewhere than where it needs to,
Yeah, so thank you very much. That's also a very excellent question, because reactive oxygen species production is very high, especially in cardiovascular systems. And what we are trying to do is basically we are developing these, for example, supramolecular assemblies. So we are wrapping them up, the graphene, in with the peptide, and the outer layer, the core shell. So the shell will be disassembled as a result of its interaction with ROS. So it will scavenge all the reactive oxygen species, and then it will start releasing NO. Because if you directly release or deliver NO, so as a reaction of NO with ROS, we will produce peroxynitrite, and peroxynitrite is highly, highly toxic. So that's not really desirable in diseased conditions. So that's why you have to have a system where actually you can control ROS first, and then you deliver nitric oxide. So that's one of the challenge for the targeted delivery of nitric oxide, especially as I mentioned for MI or ischemia, because there is a massive production of ROS. So that's why it's a big challenge, because you have to develop a kind of system which actually dual functional, multifunctional, so where actually you can control ROS first.
And so let's say you are able to achieve that. Yes. How do you still address the fact that NO for arteriosclerosis is not going to directly remove the plaque? So meaning that, as much as you add NO, like, the plaque is still going to be there, which is still going to eventually cause occlusion of your vessel. And how do you deal with then, if you add too much NO, NO tolerance, where like at some point, they're not going to be able to, NO is not going to do anything because tolerance.
Yes, because the NO is actually double-edged sword, because the high production of NO is highly toxic. So you don't want to deliver a lot of NO. And also, so that's why in in the labor room, they actually sometimes they use nitrous oxide, because just to relax the patient, the woman, basically. So because it's a vasodilator, because if you give a lot of NO, so then it is also, it's clinically established that it's highly toxic. So in disease models in coronary artery diseases, so it is clinically established based on existing precursor, NO precursors, that actually, if you deliver the amount of NO endothelial cells produce, that will be actually therapeutically relevant. So that was also the first graph in my talk. So that's how they actually discovered NO. So when actually it starts relaxing your muscles, and when it starts relaxing your vessels, so the amount of NO, how much it should be, when actually it relaxes a patient, and it also relaxes a normal human being, which actually doesn't has any disease or underlying condition.
Hi, Doctor. Great talk. I have a question about the your slides 13.3. And you use the peptide. So what kind of peptide you used in your project? Is some limitation or requirement for this peptide?
Yeah, so this is diphenylphenylene. Sorry, that's a dipeptide, and it has amine groups, and graphene oxide has carboxylic groups. So that's how we basically non-covalently attach them. So this study was basically just to start this theme in our group, to see that actually if we can make stimuli responsive, internally basically regulated stimuli. So we have done some cell work on this as well, and the paper reference is also there. But the challenges with this peptide, because we haven't studied this peptide and this supramolecular graphene assembly in animal models yet, so we don't know. But this diphenylphenylene, because it's also already used for many, like for the purification and isolation processes of proteins, different enzymes at industrial scale. So that's how we choose basically this peptide. Apparently this is biocompatible.
Other questions? Other questions? If not, let's thank the speaker one more time. Thanks, everyone.